Hi, welcome to the short instructional video about text compression with Huffman coding. At the end of this course, I do hope that you'll be able to understand the definition and identify applications of text compression, understand the process and purpose of text compression using Huffman coding, perform encoding and decoding process using Huffman coding through creation of prioritized queue and building of the code tree. The course is composed of two main modules, where I will provide you a brief introduction on data compression, particularly on text, which I will tackle the need for data compression, its two main classifications, and the actual text compression, the first module. Next module will discuss the meat of this instructional, that is, the Huffman coding, where a brief background on how did it come up will be touched. Then we'll go through the actual process of the algorithm in compressing and decoding the text. What are the advantages and disadvantages of using the Huffman coding in text compression? And finally, the different real-world applications that makes use of this algorithm. To begin with, I'll discuss Module 1, which is the Introduction to Text Compression with the following 3 lessons. Global data volume is growing by almost 60% per year, according to the diverse and exploding digital universe served on behalf of the supplier EMC. Due to this vast increase of data and files was the development of data compression that initially started in the late 40s and early 50s. Then over the years, computer systems are connected and intertwined over the network, whether local or on a wider scale, which involve exchange of data of different types and sizes. These two created the demand for data compression. Now, let's define what data compression is informally and formally. In general, data compression consists of taking a stream of symbols and transforming codes. If the compression is effective, the resulting stream of codes will be smaller than the original symbols. But defining it formally, data compression is equal to modeling plus coding. Then code for a certain symbol or set of symbols is based on a model. The model is simply a collection of data and rules used to process input symbols and determine which codes to output. A program uses the model to accurately define the probabilities for each symbol and the coder to produce an appropriate code based on those probabilities. Modeling and coding are two distinctly different things. People frequently use the term coding to refer to the entire data compression process instead of just a single component of that process. You'll actually hear the phrase Huffman coding, which is actually the main focus of this course to describe data compression technique, when in fact, it is just a coding method used in conjunction with the model to compress the data. So the two main objectives of data compression in routing the files of a file are to save space when storing it and to save time and bandwidth when transmitting it. However, it is subjected to space-time complexity trade-off. Looking at the structure and content of the files, there are actually a lot of redundancies. That's why data compression entered into the field of information theory because of its concern with redundancy. Redundant information in a message takes extra bit to encode, and if you can get rid of that extra information, you'll have reduced size of the message. Extra processing during compression and decompression imposes computational, processing time, and even financial costs. There's really no such thing as free lunch. Data compression techniques can be divided into two major families, the lossy and lossless. First, data compression concedes a certain loss of accuracy in exchange for greatly increased compression. Lossy compression proves effective when applied to graphics, images, and digitized voice. Most lossy compression techniques can be adjusted to different quality levels, gaining higher accuracy in exchange for less effective compression. Example of which is the high definition or Blu-ray movie or TV series episodes that you download, where you exchange at least 5 gigabit or gigabyte storage to a pristine and crisp audio and video quality. In contrast, lossless compression consists of those techniques guaranteed to generate an exact duplicate of the input data stream after a compress or expand cycle. This is the type of compression used when storing database records, spreadsheets, or word processing files. In these applications, the loss of even a single bit could be catastrophic. This type is the ones covered in this course and is primarily focused on text compression. Children's rhymes and stories are good examples for text compression because they often involve repeated words and sequences. So, in text compression, we have an input text string S, and what we wanted is to actually create a shorter text string S prime such that S can be correctly constructed from the S prime. So now, let's move on to our second module, which is the actual Huffman coding. You'll learn firsthand about this algorithm as we go through each of these lessons. Encoding can be simply defined as pairing characters with a particular bit pattern or sequence of numbers, octets, or even electrical pulses to form specific sets of code in transmitting data. It can be a fixed or variable length. For fixed length, just like the ASCII characters, uses the same number of bits for each symbol. In this example, the text Mississippi has 11 characters. And when the 8-bit ASCII is applied, getting the product produces a total of 88 bits for the code Mississippi. On the other hand, for variable length type of encoding, makes use of different number of bits to encode different characters, an example of which is the Morse code. However, it imposes problems on ambiguity. Just like in our example, we don't know exactly what the code is trying to convey, and it could mean different things. So how do you avoid ambiguity? Variable length codes can provide better compression than fixed length and actually avoids ambiguity. Just need to make coding is a prefix of another, an example of which is a custom prefix-free code. When coding characters using the ASCII, we clearly aren't going to be very close to an optimum method, since every character is encoded using the same number of bits. We introduce lots of error in both directions, with most of the codes in a message being too long and some being too short. It's clearly indeed that variable length would solve the issue. However, what's really the best variable length code for a given message? So in 1951, a student from MIT named David A. Huffman and his information theory classmates were given the choice of a term paper or a final exam. The professor, Robert M. Fano, assigned a term paper in the problem of finding the most efficient binary code. Huffman, unable to prove any codes were the most efficient, and he was already about to give up and start studying for the finals when he hit upon the idea of using a frequency-sorted binary tree and quickly proved this method is the most efficient. In doing so, the student outdid his professor, who had worked with information theory inventor Claude Shannon to develop a similar code. Huffman avoided the major flaw of the suboptimal Shannon-Fano coding by building the tree from the bottom up instead from the top down. So Huffman code is a statistical coding method for the construction of minimum redundancy codes. Simply on text files, just replace each alphabet symbol by a variable length code string. Not all characters occur with the same frequency and code word lengths vary and will be shorter for the more frequently used characters. This doesn't mean that Huffman coding is an optimal coding method. It means it provides the best approximation for coding symbols when using fixed-read codes. Huffman codes can be constructed using a greedy algorithm following these 5 simple steps. First, scan the text to be compressed and tally the currents of all characters. Sort or prioritize characters based on the number of occurrences in the text. And finally, build a Huffman code tree based on the prioritized list. Then perform a traversal of the tree to determine all code words. And scan the text again and create the new file or code using the Huffman codes.